All right. So the first thing we're going to do, like I said, today largely is a lot of applications. We've learned the basics of mirrors and lenses, and so now we're going to be applying a lot of that stuff. Now, we did talk previously about convergent and divergent lenses, but the lenses we dealt with, it's telling me I'm not screen sharing. Okay, I guess I'm screen sharing now. But the lenses we dealt with are very simple because they are symmetric. Like your double convex and the double concave. That's what we dealt with here. But you can have lenses shaped differently that can accomplish the same thing. All three of the examples you see at the bottom left here all have positive focal lengths. Therefore, they're convergent lenses. And then the three on the bottom right are divergent lenses because their focal lengths are negative. So we are kind of interested in what if we, combine these things together here. I mean, what if we look at some of the other examples of things, and what that might, how that might change our problems, right? So let's do that. So we're going to take a very general case here where we have two different types of surfaces, okay? And, I kind of hinted at this in the last class, but the idea is that refraction is occurring twice, technically, in these lenses. There's a surface 1 and a surface 2. Now the first surface, right, is the one that's, right here. Let me annotate this. The first surface is the first one that the light encounters. And in this example here, that lens is convex toward the object, okay? And so what happens is, just for example here, the light comes through and it's refracted. What that actually does is it bends the light a little tighter, but it's ultimately still divergent. And so in this particular case here, we're ended up with a virtual image way back here. And that becomes the object for the second surface, which is on the right-hand side here. And so when we consider those rays continuing on, then this curvature allows for a convergence, and we form our final image over here. Okay, so this is strange in a way, but we have a virtual image back here that becomes the object. So we're kind of solving two problems in a way. And we need to be mindful of both surfaces if they're not the same surfaces. If they're the same surfaces, you'll see in the equation that we're going to show that everything comes out just fine. So, here's our sign conventions for these lenses. Convex towards is always considered positive. That's true for regular lenses. Concave toward the object is considered negative. Convergent lenses have positive focal lengths. And look at this little statement down here, thicker in the center. That ends up being true. If the lens is thicker in the center, you're going to have a convergent lens then. Okay, so if we look back at the examples I showed you here, in the center, that's the thickest portion of the lens. Whereas in these, the thinnest portion is in the middle, and that will create a divergent lens. And of course, for our image location, real image is going to be formed on the opposite side of the object. A virtual image is formed if it's on the same side of the object. So this is a virtual image on the left here, but that becomes the object, and that creates a real image ultimately down over here. So there's a name for this equation. It's called there's a name for this concept here. It's called the lens maker's equation. So for any type of refractive type of lens you can create, we have this equation here. Now, the way that this is created is, and I will do an example later that will demonstrate exactly what's happening here, but this equation is formed by considering refraction at the first surface and then having a separate equation at the second surface and combining those equations together. And we got a long class today, got a lot of things to accomplish. So I'm not going to go through the derivation of this particular equation. However, one of my examples that's coming up, I'll work out a specific example that demonstrates this. So in a way, I will be doing a derivation of it later. So anyway, this is a convergent lens here. You see the P prime ends up being the object, the image from the first surface, which is now the object for the second one, and then the P double prime is the ultimate image that's formed from both of them. The N that's here represents the index of refraction for the lens here. This one is due to the fact that we always have air on either sides. In fact, this equation here is basically, the equation that we did last time, where it wasn't for lenses, it was for images through refractive surfaces. That's what that is. And it's that equation doubled to give us this one here. All right. Let's do an example right off the bat here. Okay, so there we go. The radius of curvature for the surfaces of a double convex lens. Double convex is the kind of the standard lens you usually see here. Is 10 centimeters, and the index for refraction is 1.52. So you want to know what the focal length of the lens is. All right. So now, this is not as simple as just cutting this number in half like we did for the previous things. Okay, if we're dealing with more complex lenses here, you got to work that out a little differently. So anyway, our index refraction is 1.52, so it's going to be 1.52 minus 1. And for double convex, we have two radiuses of curvature here, right? For the first surface, that's convex towards. That's a positive 10. The other one is concave toward, and that's going to be a negative 10. So that's how it looks in this one here. The first surface is a positive radius of curvature, and the second one's negative. And that's due to the conventions that we've laid out right here. Wait a minute. What is going on here? Oh, back here. So in this example here, we have a radius of curvature on the left here that's convex toward. So that's positive, but this one over here would be negative because it's concave toward the object. So let's go back to that example. All right, so I plug in our numbers here. You end up with a 9.6 centimeter focal length for that convergent lens. We can do this for the double concave. That just requires us to sort of swap the signs, because now the first surface is concave toward and the second surface is convex toward. And so everything gets sort of flipped here in terms of signs, so we end up with now a negative 9.6. So this is just the difference between these two is, well, there's not much of a difference between these two. They have the same focal lengths apparently, but they're on different sides. So. Fantastic. Let's do another example. I think the next one's an example too. All right, so for each of the thin lenses shown, and I think I have, this is example 2's in 4 parts here. We're going to go through a lot of different examples of these lenses and work out, what the focal lengths are going to be here. So let me just make sure I'm understanding everything right here. calculate the location of an image of an object that is... Okay, that's fine. All right, so we have our convergent lens here. We have two different radiuses of curvature on it. Radius on number 2 here, it's a bit larger radius of curvature. So this would be a positive 10, negative 15. So we put that through our lens maker equation to determine the focal length of the setup. Once the focal length of the setup has been established, then you go right into our traditional lens equations. So and that's really what's going on here. When you have two different surfaces, your focal length becomes more complicated. And so you should consider this as, I have this extra step to do now. Okay? If you have the extra step, go for it and take care of that. Okay, so then we put in our information for our focal length and our object distance. We end up with a 34.2 centimeters. Real image, that means it's on the right-hand side. We have another convergent lens here, except this time the secondary surface is flat, and that means we have we treat that as an infinite curvature, and so that term in the lens maker equation is 0. Okay, and your focal length is now 20 centimeters, kind of what we are used to, right? Radius of curvature. Get our focal length from that. Well, that's actually not similar at all. Never mind. That's confusing. Anyway, so we put it through here. We get our focal length of 20 centimeters because of this. I mean, that flat surface actually produces a different kind of focal length. So, and we put this through, and we end up with is there supposed to be a decimal point there? Because that seems absurdly large. Although we are close to our focal length. Let me just double check that. I mean, it's probably right, because, you know, when you're close to your focal length, your images are formed extremely far away, because the definition of focal length is, like, you know, if something's at infinity, where it would come to a focus. So let's do 1 over 20 minus 1 over 18.5. I got a feeling this is going to come out to be crazy high. It is. All right. So this is a virtual image. We are under the focal length, right? When you're closer than the focal length, you're getting virtual images. And this thing is far away. This thing is almost 2.5 meters away. That's where it's going to come to a focus. So that's nuts. Let's look at the divergent examples. So in the divergent example, we got a 10 and a 15. So the first one's a negative 10, the second one's a positive 15. We put that through our equation. We get a focal length that is minus 12 centimeters. So it's kind of a sanity check here. If you're working this stuff out, your divergent lenses should always come out negative, right? Convergent always come out positive. The focal length here, our minus 12 centimeters goes in here. Now, we're at 18.5 centimeters. Now, when you have a divergent lens here, though, you're always going to end up with something that's ends up being negative here. So if we move that over to the other side, that S there, negative, yeah, that's negative. So we end up with a negative 7.28 centimeters. So that is a virtual image, and it's going to be formed on the same side as the object. Same side as the object. So the rays come in and they diverge away, you trace back, and you go back to 7.28, you got your image there. Fantastic. Now, this one here, for our divergent lens, we got two things that are concave toward. So they're both negative radii. These are negative 10, negative 15. We end up with a negative 60 here. All right, object's at 18.5. So we put that through the equation, we get a negative 14.1. Again, virtual image, same side, good stuff. We got it. All right. Let me think here. That's it. I mean, if you had to work out like magnification stuff, it's the same way you do with lenses. Okay, it's the same way you do with lenses. In fact, like I said, when you're dealing with, you know, more complex lenses here, just consider this as I have an extra step. I got to figure out the focal length. All right, good. Good. Woo. Oh, that's what I kept forgetting to say. Sorry. We never talked about radius of curvature when we introduced lenses. That's why. All right. No, we did that for mirrors. We did not do that for lenses. In fact, you notice we left that ray out. You know, when we did lenses, we had 3 principal rays. I forgot. Yeah, we didn't talk about the radius of curvature because it turns out it's a little bit more complicated, and that's what you're seeing right here. Okay. This is meant to be our in-class activity, but we're not in class. We're sitting inside our houses. Or maybe you're driving. Or maybe you're sleeping. Or whatever. But this one's just a straightforward convergent lens, 2 concave toward. Sorry, this is, let me annotate this. I got to redo the slide because it's right. It's right. This is negative here. This is negative, not positive. And then this becomes positive here. And then we get our 80. Let me just do it again because I'm going insane right now. Right, 0.5. Flip it, 80. All right, sorry, I got to fix this slide here. This is negative. They're both concave toward. I should be adding here, getting 80. It's positive in the focal length, and it is thicker in the middle, so it's a convergent lens. But ultimately, you know it because of the focal length here. All right, not good. 2 lectures in a row, messed up my examples. Okay, let's do lenses in combo now. Yeah, let's look at now. Here's the example I was telling you about earlier: a combination of lenses. So I've said this a million times, and I'll just say it again. But the image formed by the first lens will act as the object for the second lens. So you're really kind of solving 2 problems here. This is a basic example of your like a telescope. You have an object that is very distant, and we have a objective lens that brings us down to a focus and creates an image here. That becomes the object for the eyepiece. However, that is creating a virtual image because the rays are going to diverge away here. And so what happens, though, is when you put this, the image that's formed here very close to the focal length of the eyepiece, you create this big magnification, and you create a virtual image that's seen very distantly. And so this is the image you end up seeing if you're on this side, because all these rays converge to this point over here. But, you know, there's 2 problems to solve here. Where's this image being formed from the first objective? And then that becomes a new S for the eyepiece. Okay. So let's do an example of that. Okay. Let's, we have convergent lenses A and B. Oops. Convergent lenses A and B have focal lengths 8 and 6 respectively. They are placed 36 centimeters apart. Both lenses have the same optic axis. Well, I hope they do, because that's a little bit of a nightmare right there if you don't have the same optic axis here. Object 8 is 8 centimeters high and placed 12 centimeters to the left of the lens. We're outside the focal length. That's nice. So let's do it. Now we're given the focal lengths for these lenses here. So we don't need to know the details about the lenses. They can just be standard, like, you know, double convex or something. But we're already told the focal lengths here, so that's not an additional issue we have to do. So I do my lens equation for a focal length of 8 and a distance of 12. I put that through my lens equation and I end up with an S prime of 24 centimeters. Now 24 centimeters means I'm on the right of that lens, okay? And if you compare the distance between them, 36 centimeters, we can see here that if this is going to become the object for the second one, then the value of S for the second one is going to have to be 12 centimeters, right? Because the idea is that, you have something like this. You have, you have a lens here. Oh, I've got to annotate that, don't I? So you got something like, you got like a lens that's here, and you got another lens that say it's over here, and this one creates an image that's right there. So that's your 24 there, and that means this must be 12. So you have your object here, it's inverted or something, right? What is it? Let's go down a little bit here. So you start it off being what? 12, you're off 12 over here. Something like this. And then we end up with an inverted image that's twice the size, looks like. Right, because it was 8. Yeah, twice the size. So now, when we come over to here to do lens B, we got a different focal length. You have to be cognizant of the distance between the lenses to figure out the new position. It's 12. Your Y value is now negative 16 centimeters because you have this inverted image. So we go through the lens equation again. We work out what the new object distance is. It's 12, which is interesting. It's exactly the same distance away. Why is that? Oh, it's because the focal length and the because we're twice the focal length. That's a similar thing to the radius of curvature, actually. But anyway, so we put so that means there's no magnification then. It's going to be the same size, but now it's going to be upright. And so the 16 centimeters is the upright. So the final image is 12 centimeters to the right of lens B. It's an upright image twice the size of the original. So nothing too complicated really here. Nothing too complicated. But the one thing is you got to be able to bridge the two lenses together. And that's by figuring out, okay, what's my focal length? Sorry, what's my image distance? And then being able to produce the correct object distance for lens B. And, what do you think happens? How do you think people mess this up? Well, let me tell you, because I've seen it plenty of times. What they do is they get this number 24, and then, boom, that's automatically their object distance. And that's not the case. It happens a lot. You got to do a little bit of thinking here to determine the new object distance. All right, that's a great problem. That's a great problem. All right. Let's keep chugging along here. Yeah, let's keep going. Keep going. All right, so let's start looking at a bunch of applications here and sort of see how all these principles apply to very simple optical instruments. The first example that we can do is looking at a standard camera. The way the camera is going to work here, it's typically a type of lens. Sometimes it's doubled up, sometimes it's not. But what's happening is we have a detector back here. Could be film, could be your CCD. The image gets formed onto there. So we got to be very mindful that the camera aperture and the position of the lens is adjusted so that the focal length, so that the focus, I should say, right, lies on the detector. Okay, and so that does require you to adjust things a little bit differently. And if you have a compound setup here, and that's how you can get different zooms on your lens on the camera, because the two lenses will work together to produce, an appropriate magnification, seeing different fields of view, basically, which is what we mean by zooming. Okay, and the combination has an effective focal length to it. So we take the two lenses there, we combine what they're doing to come up with this single focal length that we prescribed for the camera. So here's some nice compound things here. So in the examples that you see here, we have a convergent and divergent lens here. And what that's doing here is the convergent lens creates it creates this convergent beam of light, then it hits the divergent lens, and then it doesn't converge down as quickly now. And so that ends up being the focal point for that convergent lens with that in the middle there. You can adjust the distance between these things. If we adjust this divergent lens a little bit closer, then what happens is that convergence takes a longer distance to have, and you end up creating a much larger focal length. These two lenses down here are sort of the effective single lens in this combination that we have here. And so you can easily change your focal length. So normally you have a single lens, and you got a set focal length based on how it's made. But the combination of these two allow you to create an adjustable focal length, which is helpful in a camera when you want to see things at different distances. The combination of these things will allow that. So that's nice. So, question for you here, see if you're fine. I have a lot of questions actually now. Parallel light rays we focus at a point. What's the answer here? Closer to, same distance farther from the second lens, then light would be focused by the second lens axial lobe. What do you think's happening here? Oh, my goodness. So put a letter and you think you got it. What do you think's happening here? So first thing to consider is what's the light going to do when it goes to the divergent, then what happens when it goes to the convergent. All right, C's. Great. Yeah, so what happens here is, the convergent lens is going to have some focal length. But the divergent lens is going to make those rays open up more, given the appearance that the object is coming from some location back here. And what ends up happening is that image gets formed further back. So it's going to appear that it's farther from. That's the idea. Okay. Because these light rays coming in here, that means effectively you have an object that would be at infinity. So it comes down to this focal length. But anything else would have something that's a bit further out. So, great. Right, so let's do the problem here. You got a digital camera lens. Your digital camera lens. The effective focal length of 10 millimeters is focused on a flower 20 centimeters away. Then you turn to take a picture of a distant landscape. How far and in which direction? All right, cool. So the idea is that you have your focal length, effective focal length, right? The combination of the lenses in there, and you're at 20 centimeters. So we're going to have to figure out. Well, let's just get to it. I have the slide for a reason here. So if we're considering the flower, okay. Now, check the units out here, right? This is millimeters for the focal length, and the flower is 20 centimeters away. So we use our standard lens equation, because again, the combo of the two produce an effectively same, convergent lens. So we got 10 millimeters for the focal length, and we got 20 centimeters for the object distance, and that produces an image distance that's 1.05 centimeters. Okay, so that's from where the lens is, to where the image is done. Now, if instead we look at the landscape, that means we have the object effectively at infinity. I mean, when we say distant landscape, you know, you don't see a number there because that's sufficiently far away that we're not really going to get, you know, anything substantially different than if we just put infinity in there. Okay. So look at this though. If we're looking at something distant, then we expect the image to form at the focal length. Focal length is 1 centimeter. So if S becomes infinite, then S prime and F become the same thing. So we were very close to the focal length, which makes sense because we're 20 times farther away from our object compared to the focal length. So that's pretty far away. So that image has got to form pretty close to the focal length. So that's cool because look what you have to do. You have to basically change where the lens is located by what? Half a millimeter? That's it. And we can look at something that's 20 centimeters away, and then we can instantly look at something that's, you know, a mile away, right? And the difference was half a millimeter. Okay, half millimeter, that's it. And that's the beauty of the camera, is that you have this compound setup where you can make slight adjustments to the distances between the lenses, and you can focus on anything you like. So pretty cool. Pretty darn cool. All right. Now, there's other aspects to this camera, though, that we want to look at. Other aspects. You know, if you have a camera or you're into photography at all, you're probably familiar with a couple of these concepts here. In particular, F numbers and stops and things like that. So we don't get much into the intensity of light. It's kind of a topic that's related to more E&M kind of stuff. So I'll simply state a relationship, and we won't go any further than that. But adjusting the aperture of your camera controls the amount of light that gets through. And the F number is sort of a light gathering ability, and it's a ratio of focal length to diameter. And the intensity of the light that you get goes as 1 over the F number squared. And so what happens here is when you have say you have a rather large F number, a rather large F number can come from the fact that you've lowered the diameter quite a bit of the aperture, and you don't let a lot of light through. That's the issue with that. And that's maybe appropriate for conditions, right? So different conditions on what you want to take. And in lower light conditions, you may want to open up your aperture more, but the issue with that is, well, opening it up less makes things fainter, but then you have an issue with things moving and blurring in images and stuff like that. So there's always got to be sort of a balance between what you're trying to see and how fast things move and things like that. So anyway, question for you with this. If the F number of a camera lens is doubled, say from f4 to f8, what's that mean about the diameter of the lens aperture? How much has it increased or decreased by, going from 4 to 8? Assuming, obviously, that our focal length is set. We set the focal length. What's going to happen? Okay, C's are good if you said C, because, again, the definition of the F number is focal length over diameter. So if the F number went up, it means the diameter went down. It went down. Okay. And if it went down, if your focal length, if your F number doubled, in terms of intensity, all right, in terms of the intensity of light would go down by 1/4, because having a larger F number, you know, the aperture lowered, and so you're getting in 1/4 of the amount of light that you normally would get. All right, so this is just ranges of f-stops, and we want to see what the range of apertures and intensities are going to be here. So let's look at that. All right, so we got a common telephoto lens for a 35mm camera. The 35 doesn't matter, that's the film. That's not related to the optics. But the focal length of 200 millimeters is related. And so if we have different f numbers, 2.8 all the way to 22, we can give a range of diameters there. So you just basically plug in, you solve for d in the f number equation. We get 200 over 2.8 gives us a 71 millimeters, so very, very wide, right? And then the large f number ends up having a very small diameter. Okay, and then in terms of the intensity of light, you can take a ratio of those numbers. Obviously, the one that's larger collects more light, but it turns out here we do a ratio of the square of these numbers, we get around 62. So that means that the 8.2 stop can collect 62 times the amount of light than the other one does. And then what happens is if you want to, in terms of time now, if the 22 needs to spend 62 times longer to collect the same level of light, well, that can be an issue if things move around, right? So you got to be mindful of level of light, what kind of action are you looking at? Is it a calm landscape? Is it somebody moving very fast? Trying to image things where things are moving fast and the light is very challenging to do. So anyway, okay. The human eye. So the human eye has an adjustable lens in it. And there's actually a couple different aspects of what your eye is doing. There is the cornea, which is the layer that covers up, protects your eye. And then there's a fluid called the aqueous humor between the cornea and your lens. Then you have your lens that is attached to muscle fibers that can allow it to contract or expand. Then it passes through what we call the vitreous humor. Now, those things are effectively water. In terms of their index or refraction, I should say. And and so what happens is light enters a combination, what effectively is a combination of a lot of different materials. I mean, there's effectively 4 different types of materials that the light's going to go through, and that eventually forms an image on your retina, which is picked up by the different rods and cones on your retina that's sent as an electrical signal to your brain through the optic nerve. Yeah, what you have here is you got your, it's called ciliary muscles here. And these things are nice, except when you turn 40, and then they start to just not work as well. I remember I saw an optometrist about 3 years ago, and they said, I got a problem seeing things up close now, because my vision, I'm nearsighted, so I can't see things that are far away, so I really depend on my nearsightedness. But now, when I look at something, like this close, I see it. And I told my optometrist, I'm like, what's going on there? And he's like, how old are you? I'm like, 40. He's like, yeah, that sounds like 40. He's like, thanks a lot, doc. He's like, it happens to everybody. Right around 40, those muscles start to weaken, and then you start to lose a little bit of your nearsightedness. So anyway, the idea is that this adjusts. These muscles adjust the lens and create, the focal length you need to see things clearly. But it has a pretty wide f number. You can see here, 3 up to 16. That's quite a bit. That ratio, right? What's that ratio? It's like 5. So that means your eyes can adjust to get almost a contrast difference of about 25. And then you can also take into account that you can squint and use your eyelids to effectively reduce your pupil. So It's pretty nice. This is amazing. In fact, what's amazing about the eye here is that humans have not created an eye, in the sense that your eye has the ability to detect things from about 400 to 700 nanometers all at the same time and spatially recognize things. I mean, normally if we have color images, it's because we have multiple images being taken to produce the kind of color that we see. But having the kind of resolution, both spatially and spectrally, is very challenging. And at least to my knowledge, I'm not aware that we've accomplished the equivalent of the human eye in terms of having both spatial and spectral resolution that matches the eye and the contrast ratio that the eye can have. It's pretty nice, pretty powerful stuff. So, all right. Oh yeah, I gotta scroll. Yeah. All right, so when your muscles tense or relax, we call this accommodation. And accommodation is what it sounds like. Your eye is trying to change the focal length of your lens to allow you to see things more, that things are in focus. So that word we're going to be using a little bit here to describe things. All right, so the farthest distance that the eye can see we call the far point, or FP. And you can focus on objects that are extremely far away. In fact, there really is no normal limit to a person's far point. I had said say about that. Oh yeah, I mean, assuming that you have, the eye has an inherent resolving power to it. Normal human eyes have a resolving power of 1 arc minute. An arc minute is pretty small. If you were to hold up, I don't know. Let's see, maybe this pencil. If you held up this pencil, 10 meters away. Is that no? That's not even an arc minute. So, but that's normal resolution of the eye. So, assuming you could see kind of detail, you should be able to focus on it. That's the far point. Near point's different. There's a limit to how close you can have things to your eye where your eye can actually accommodate that. And for most people, that distance is about 25 centimeters. You put things closer than 25 centimeters, it becomes a little bit more challenging to see. Your eye has the ability to focus things, so that's what we treat as the near point. So my near point, that's 25 centimeters. 25 centimeters is 10 inches or so. 10 inches. I don't know. All right. Keep forgetting to scroll. All right. If the near point of your eye is at 75 centimeters and not 25, what do you think that makes you? Nearsighted or farsighted? The answer is not C. It. What do you think that does? If your far point is actually at 75, a lot of bees. Yep. Because what happens now is you should be able to focus things that are at 25. But if your near point's 75, well, that's the closest something can be without corrective vision that you can see. So, now, here's where corrective lenses come in. If your near point's at 75 centimeters, you can use a corrective lens to take an object that, say, is at 25 centimeters. What you're supposed to be able to see at 25 centimeters, right? What the lenses do, the lenses take that image and it pushes it out to 75, which your eye can adjust to, and then you can see it. So that's what the corrective lenses are doing. They're trying to take your true near point and put the objects at where they're supposed to be. And we'll look at some examples of that here. So when you get contacts or glasses or something, they're usually indicated by what's called the power of the lens. They don't talk about focal lengths, and they don't do that 20/20, 120 kind of vision stuff anymore. My box of contacts has got numbers on them. They're negative numbers because I need divergent lenses in my eye. Because I'm I used to be nearsighted, but now I'm neither-sighted. That's the word I use for it, neither-sighted. But the power of the lens is given by 1 over the focal length of that lens, and it's given in units of inverse meters. So if a lens has a focal length of 50 centimeters, we say it has a power of 2, because we convert that to meters. And that's really what you see here. You see a prescription that, well, you either get a prescription for nice spherical lenses with, with some kind of power on those, or you have astigmatism, which is a little more complicated. I got astigmatism in this eye, my right eye, and astigmatism is basically kind of like the lens maker equation, where the lens is more complicated and the orientation of the lens matters a lot. It's actually shaped in such a way to fit on your eye in a certain orientation. There's an axis on it. So when I put my left contact in, I just can put it in whatever I want, but the right one, I got to look for this little line, which is very hard to see because my vision's already cruddy. Wish I had a better system than just giving a little line that you're supposed to somehow see, which is impossible to see, but anyway. All right, so the cause of having farsightedness, which is the opposite of myopia, it's hyperopia. Hyperopia, I don't know how to say this word. Hyperopia? It's not pronounced hyperopia. That sounds silly. Hyperopia. Let's see. I never knew what this was. I'm going to find out right now. There we go.
Hyperopia.
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 Hyperopia?
Hyperopia.
Hyperopia. All right. Nice to know. Usually when you see the word hyper in there, you don't pronounce it that way. You say some weird thing. Hyperopia. I don't know. But it's hyperopia. So I got to remember hyper and rope. But what ends up happening here is the eyeball becomes misshapen over time. And so, like in this example here, the eyeball is shortened, basically. And so when light is supposed to come to a focus, it doesn't hit where the retina is supposed to be. It ends up hidden in an area that's closer, which means the light is unfocused. It should be back a little farther. So, so what happens here is the eyeball is just basically too short. And the eyeball needs to be longer in order for the refraction to actually come down to a focus here. So the image is blurry at this point. But the idea is that for hyperopia, is that your near point is not where it's supposed to be. You still see things far away, so your far point's still infinity, fine. But your near point's not 25. It's greater than 25. And so you have to have some kind of corrective lens that allows you to create effectively an image that puts it where it's supposed to be. Okay. So here's an example of that. If the image that you're getting is not hidden in the back of your retina as a focused image, you have a corrective lens that can help it come down to converge much more rapidly. Okay, right now the convergence is not fast enough, so to speak, to hit the back of your retina. So you have a corrective lens that allows that to converge down more rapidly. And the convergent lens here forms this virtual image that's way back here. Okay, the eye wants to see this. What happens is the lens gives the appearance that it's further out, and then your eye can provide accommodation for this by having this lens basically produce an image that's out here. It's a virtual image, and it's much farther away, but that's fine because your eye can work on things that are farther away. So what they're basically doing here is if your near point's not at 25, the lens adjusts things so that your near point becomes 25. That's the idea behind that. Okay. So Gregory has hyperopia.
Hyperopia.
Hyperopia. All right.
Hyperopia.
Okay. I'm sorry. Don't repeat it. I made a mistake. Okay. Near point of his left eye is 150 centimeters. I don't know what's up with why just one of the eyes are doing that, but whatever. Well, I mean, they can be different, I suppose, yeah. What prescription lens will restore normal vision? All right, let's see how this is done, because here's what we're going to do here. That's where we need to put things. Way out there. Because this thing's at 25, not seeing them. You got to put them out at 150. So your near point's being thrown out there. That's the idea. So let's see how this example works. All right, normal vision is the near point of 25 centimeters. So what's going to happen here is the near point's at 150 centimeters. So our object, right, that we're interested in is going to be at 25. The image, however, will be virtual, so it's negative, and it has to be put out to 150 because we can't cut it at 25. Our eye doesn't accommodate, but it can accommodate out to 150. So that becomes our our image distance here for the object that's placed at 25. So we put these numbers in here, we end up with a focal length of, wait a minute, what did I do here? Oh, I didn't solve for the focal length. Oh, I didn't solve for the focal length. Okay, Anyway, the power is 1 over the focal length. So here, when we subtract these numbers, you get 0.033 centimeters. Got to convert that to meters, though. So in meters, it'd be 3.3. Remember, these are inverse units here, right? Inverse units. So the numbers go up. And so the lens power has to be 3.3. So you can now see things at 25 centimeters because the lens is placed on the object way out at 150. Okay, so that's effectively how that works. Let's see short-sightedness. All right. Oh, I can use my buttons again. Oh, I'm so excited. All right, myopia is caused with an eyeball that's too long, meaning that the image comes to a focus first before it hits the back of the retina. You have the opposite problem. You can see things up close just fine, but things that are at a distance are different. Your far point is not at infinity now. So you can't see things that are very distant. But guess what you're going to do? You're going to create a lens that takes our objects and effectively places them at your new far point, so you can see them. So, but the idea here is that we did the far-sighted stuff, your near point's not 25, it's farther away. Here, your far point is not at infinity, it's shorter, so you need to make a correction there as well. So, you have to create a lens. You see a divergent lens here. I guess I have convergent lenses. I thought I had divergent lenses. That's strange. Oh, wait. Oh, no, I do. Sorry, I'm mixing myself up here. Yeah, myopia seems... Oh, yeah. Okay, so... Yeah, you can't see things far away. This is nearsightedness. Okay, sorry, I got confused for a minute. Yeah, I don't see things far away. So this is a diversion lens. And what that does is that object, we want it to be like it's at, the object's at infinity. We can't see that. So we have a divergent lens here that makes the object appear that it's a bit closer. It's a virtual image, but it's, we set this to be whatever your actual far point is. So let's do an example with that. Mark has myopia. It's true. Far point of his left eye is at 20 centimeters. 20 centimeters? I mean, 200 centimeters. That's still pretty far, isn't it? Anyway, what prescription lenses will restore normal vision at? Okay, so that means the object we want to see is at infinity. But we need to make the image at our far point. So it's going to be at negative 200 centimeters. Okay, so we're bringing the image to 200 centimeters so that the eye can work. So we put that through here. S is, 1 over S is just 0. And so we flip this, we get 0.5, a negative 0.5 inverse meters. So the lens power is negative 0.5. My goodness. Because mine is, my lenses are around 6 point something. So I think 6.25 is my worst eye. My worst eye is the one over here, actually, my left one. Let me flip that. Oh, brother. Wait, that doesn't make any sense. 16 centimeters? No, that's not right. What about 5? What? How am I even able to see here? Anybody know anybody who has contacts or prescription? Anybody know theirs? No? Nobody? Yeah, mine's around 6, I believe. Okay, so we're both... Oh, yeah. Oh, you got LASIK. Man. Well, you got LASIK, I got kids. That's where all my money goes, unfortunately. Too many kids. What's going on out there? Delivery? Yeah, I think one's... Anyway, well, even a 5... You're kidding me. 2020 at 41. Oh my gosh. I'm a little jealous, actually. Eat your carrots. That's what I heard. Yeah, no, my vision started to decline when I was 9 or 10. That's when because I would sit. When I sat in class, I couldn't read the board, so I kept asking teacher, can I sit up closer? So she sit me in the front row, and I'm like, still can't see it. And she's like, you ain't right, boy. Get your eyes tested. So I did. And I wear glasses. So, oh well. Okay. Let's get back to it. That's nice. That's nice. If I'm gonna get that, I gotta get it soon. I think there's a window of opportunity for that on 2 fronts. My vision hasn't changed much recently. That's good. But I think I thought there's like an age limit. Now, when I say limit, I don't mean limit. The older you get, the less successful and the less correction you can be given. I don't know the details, but I don't think I'm getting LASIK anytime soon. All right, let's keep going. I think I only have a couple more things to do here. What time is it? Good on time. Good on time. All right. So, say you got a lens that looks like this. What's going on here? What do you have if you need lenses that look like this? All right, D. Well, thank you. It is D. You were paying attention the last 10 minutes. All right, we're going to look at a couple other compound things, microscopes and telescopes. All these are compound instruments. Okay. What microscopes are trying to do is take smaller objects and produce a giant magnification for them. But it's a two-part thing. You got an objective, and you got an eyepiece. And the major part of the objective is to create an image for your eyepiece. The eyepiece largely controls the magnification. You can adjust the focal length on an eyepiece very easily. You can swap out different things with those. So what you see here is we have different objective lenses, actually. So we can actually swap out in that sense. And then we have our eyepiece here, which can have an adjustable length to it. But it's it's a compound setup here. So here's an example of that. So what we have here is we got our object placed near the objective. And one of the things that happens here is that the focal length of the objective and your image distance are very close to each other. So you end up creating an image that's very far away from the focal length on the other side here. And what happens is the tube that the light's transmitted through, basically the effective distance between the objective and the eyepiece, which we'll call the tube length here, produces a image that is effectively at the focal length for the eyepiece. And what that does is it creates a highly magnified image that is seen through the eyepiece. So here, the distance S is very small, and the image distance ends up being very, very big here. And so we create a large magnification when we do that. Now, in our setup that we have there, if we look at the objective, magnification is given by S prime over S. Now, S prime is very long, and it is effectively the length of the tube. Okay, whereas the object distance is placed at effectively the objective of the focal length of the objective. So when you combine what the objective is doing with what the eyepiece does, you get your overall total, what we call angular magnification. So the first part here is what's going on with the objective. The second part here is what's going on with the eyepiece. Your object is placed effectively right on the focal length of the eyepiece, and then the image is set so that we're at the near point of the eye. And a lot of lengths are sort of established for microscopes. They have sort of standardized length for them. So we can see here that you can create the kind of magnification you want by simply adjusting your focal length on your the focal length for the eyepiece and the objective, which you saw back here can be done by, for the objective, you can swap out different eyepieces here and eyepieces up here. And so that basically determines what that's going to look like. So let's do an example of that. So where is that slide? Here it is. So we're looking at blood cells. That's supposed to be the picture here. And we're trying to determine, what's effectively the size of these when you look at them through the telescope. Now, the blood cells are on average, microns in size. We're going to take 7 microns as our diameter for the blood cells. But we have a 40 times objective and a 10 times for an eyepiece. And so what we end up getting here is we multiply those together, we get a negative 400. So this image is flipped, but it's 400 times larger. Okay, the objective is able to magnify things by a factor of 20, again, because we're putting our sample very near the focal length, so it creates a huge magnification. Likewise, when the image is formed, it's placed very near the focal length of the objective, so we end up with this very large value for magnification. So if we have a 7 micron diameter human blood cell under the microscope, it will be flipped and it will be approximately 2.8 millimeters. That's how it will appear to your eye. It will look the same as an object that is 2.8 millimeters. That's simply by combining those two magnifications together. Okay. Now let's look at the telescope, and then we'll be done. So, the telescope is a very similar setup. It works very, very similar to what the microscope does. The image distance here is going to be set very close to the focal length of the objective. And the focal length of a telescope is very long. The focal length of a if you talk about with the lens in it, I'm talking about, when I talk about telescopes, this is talking about lenses, not mirrors. Mirrors is a separate thing. I mean, you can go through that too, but I'm just talking about your traditional Galileo kind of telescope. The eyepiece is really just the magnifier on the, just like for the telescope, it's largely controls the magnification. And for the magnification of the telescope, it's a ratio of the focal lengths. Okay, and the images are flipped, but it's a ratio of focal lengths. And that ultimately comes from looking at, do I have a picture here for that? I think I do. Or maybe I don't. Well, I'll go back and talk a little bit more about this. Because this right here, this magnification, this is the definition here. It's how large something appears to your eye, right, compared to how large it actually is. And that can be related to focal lengths. But I have to show you a picture for that, and I don't have that picture before. Well, I have to show you this first. So if you're choosing lenses for a telescope that you will look at the moon and the planets, you should select what? What's the best kind of selection for focal lengths that you should do here? Well, I'll just tell you. The answer here is B. B. You want an objective with a long focal length and an eyepiece with a short one, because if you look back at this ratio here, you will try to make the angular magnification large. Large focal length is good. That's why you typically see telescopes very long, and your eyepiece focal length needs to be very short. But you don't necessarily want a high magnification, because if your telescope isn't so good at collecting light, magnifying objects generally produces really blurry, faint images. There's kind of a sweet spot where the resolution of the image matches the resolution of your eye, and that's kind of the most optimal thing in terms of brightness, detail, all that stuff. It's unfortunate because a lot of commercial telescopes advertise absurd magnifications, like just completely absurd magnifications, that if you ever were to attempt that and you looked at a planet or something, you probably wouldn't even see anything because it would be so magnified, not out of focus, but so magnified and blurred, basically, because you're not collecting a lot of light when you do that. So, but here's the compound eyepieces here, or compound lenses, I'll say here. You have your object that is effectively at a distance of infinity, okay? And it comes in, that's focused by the objective, which then diverges away after the focal length and becomes a virtual image seen at, basically infinity here. So the idea is that this objective focuses things down to effectively match the eyepiece's focal length. And then the object appears as a virtual image very, very, very distant. So this angle this is what I was trying to describe before, this angle here, this angle is your, the angular size, how things actually look. And then when things are focused by the telescope, you have an eyepiece that produces rays of light that have a slightly different angular size here. And these are ratios, basically. Think about a triangle here. The hypotenuse, the outside opposite is h. The adjacent side is your image distance. You have a similar thing here, where this is your image distance here related to this height. So the h's drop out, and it turns out that the ratio of angular sizes relate to the focal lengths because they're part of the geometry of this. That's why we have this relationship here. This first part's the definition. The second part, though, can be derived by looking at like similar triangles in the setup here. All right. Not going to say much about reflecting telescopes. I have really nothing substantial to say about that. I think we have one last question here, and I think we're done. So why don't you chime in on this question here, and then I get to eat whatever food I currently smell right now downstairs. Somebody's cooking something good, so I'm happy about that. So what are we doing here? Increase the diameter of a telescope's objective. That's nice. With no other changes. All right. What do you think's going to happen here? I like B a lot. It is B. It is B. Because magnification does not depend on the diameter of the objective. It depends on focal lengths. It depends on how your lenses are. But you do collect a lot more power. You collect a lot more light. Your light gather power increases. Also, your resolvent power of your telescope increases as well. But magnification is not determined by the diameter of the objective, unfortunately. All right, so this other stuff here is stuff I don't really normally talk about. So we are done. So here's what we're going to do. I won't see you again till, I may not see you for a whole week, actually. But normal stuff's going to happen here. Work on the study questions. If you have questions for me, I have office hours tomorrow in the morning. But I can be on a lot of other times. Shoot me emails for questions. I will be on during class time on Monday. I'll just be on Zoom just doing grading or something if you want to come on and ask me questions about things. But make sure you get the homework in. Otherwise, have a fantastic night and weekend, and good luck on your exam.